Given a square matrix A, which has the same number of rows as columns, a non-zero vector in the vector space of R tuples is called an eigenvector of A if the product of matrix A with the vector V is a scalar multiple of V for some scalar lambda. So the scalar lambda is the eigenvalue of the matrix A, and V is an eigenvector corresponding to that eigenvalue. So noting that a matrix can have multiple eigenvalues, and there can be multiple eigenvectors corresponding to a single eigenvalue. And note that we impose the restriction that the eigenvector be a non-zero vector to avoid the trivial case of the matrix A multiplied by the zero vector is equal to lambda multiplied by the zero vector. So this equation is satisfied for every A and lambda. So recall our equation of A multiplied by a vector V is equal to lambda by V. So if A is some square matrix with the same number of rows as columns, so multiplying lambda by the identity matrix, we don't alter the right hand side because lambda by the identity matrix by the vector is the same thing. And then if we subtract lambda I from both sides, we get A minus lambda I multiplied by the vector V is equal to the zero vector. So you may recognize this as a homogeneous system of linear equations. So we have a matrix multiplied by a vector is equal to the zero vector. So as we know, if the inverse of the coefficient matrix exists, then we only get the trivial solution because we have the inverse by the zero vector. So therefore, for non-trivial solutions to exist, the determinant of A minus lambda I must be equal to 0. So the inverse of A minus lambda I does not exist. And this is called the characteristic equation of the matrix A. So let's find the eigenvalues of this matrix by using this condition. So we want the determinant of A minus lambda by the identity matrix. So for this 2 by 2 matrix, lambda I is going to have lambda on the diagonals and 0 everywhere else. So A minus lambda I is going to give 3 minus lambda and 1 minus lambda on a diagonal, and then the other entries remain the same. So to calculate the determinant of this 2 by 2 matrix, we have 3 minus lambda by 1 minus lambda minus 4 by 2. So if we expand and simplify, we have lambda squared minus 3 lambda minus lambda plus 3 minus 8, which is minus 5. So this here is the characteristic polynomial, which we denote P of lambda. And this polynomial has a degree R, corresponding to the number of rows or columns in this matrix. So in general, the characteristic polynomial is equal to lambda to the power of R plus some constant by lambda to the R minus 1 plus another constant by lambda to the R minus 2, and so on up to the final constant CR. So we equate the characteristic polynomial with 0, so we can factorize this polynomial, being lambda minus 5 by lambda plus 1. So therefore, the eigenvalues of the matrix A are lambda 1 is equal to 5, and lambda 2 is equal to minus 1. So note that when we equate the characteristic polynomial with 0, a polynomial of degree R has at most R distinct roots. Noting that we can get a repeated root for some characteristic polynomials. So effectively, P of lambda is equal to 0 has at most R distinct solutions, and therefore an R by R matrix has at most R distinct eigenvalues. And we're focusing on real eigenvalues for now, but they can be complex, which we'll cover later on. As we mentioned, eigenvectors are non-zero vectors that correspond to an eigenvalue of matrix A, and they satisfy the following equation. And we saw this written as A minus lambda by the identity matrix by the vector V is equal to the 0 vector. So effectively, the eigenvectors are non-zero vectors in the null space of A minus lambda I. And we call this null space the eigenspace of A that corresponds to the eigenvalue lambda. Or another way to state this is the null space of A minus lambda I is the solution space of this homogeneous linear system. So we previously calculated the eigenvalues of this matrix. So writing this equation corresponding to the first eigenvalue, we have the matrix A minus lambda I. So we subtract lambda from the entries on a diagonal. So 3 minus 5 is negative 2, and 1 minus 5 is negative 4. And the off-diagonal entries remain the same. So let's multiply by the vector with components v1, v2, which is equal to the 0 vector. So if you augmented this matrix with the 0 vector and then solve this linear system, so let's do that. We have minus 2, 4, 2 and minus 4 augmented with 0, 0. And therefore if we add row 1 to row 2, we get zeros in the bottom row. And therefore our solution is minus 2v1 plus 4v2 is equal to 0. And therefore if we let v2 equal t and solve this equation, v1 is equal to 2t. So therefore we can write the solution as v1 v2 is equal to t by 2 1. So this is the solution space, or the eigenspace, corresponding to this eigenvalue. And this eigenvector with components 2 1 forms the basis of this eigenspace. Now for the other eigenvalue, which was minus 1, again we subtract lambda from the entries on a diagonal, so 3 minus minus 1 is 4, and 1 minus minus 1 is 2. And then the off-diagonal entries remain the same. So we have v1, v2 is equal to 0, 0. And in a similar way, if we solve this system by Gaussian elimination, we get 4v1 plus 4v2 is equal to 0. So v1 is equal to minus v2. And then setting v2 as the parameter t, then v1 is minus t. And we can write the solution as v1 v2 is t by minus 1 and 1, which is the null space of A minus lambda I, or the eigenspace of A corresponding to this eigenvalue. And this is the basis vector for the eigenspace, being the eigenvector with components minus 1 and 1. If V is an eigenvector of the matrix A, then multiplication of V by A leaves the direction unchanged. So for example, if we multiply the matrix A by this eigenvector corresponding to this eigenvalue, then we have 3, 4, 2, 1 multiplied by 2, 1. So 3 by 2 is 6, plus 4 is 10, and 2 by 2 is 4, plus 1 is 5. Which is the same thing as 5 multiplied by 2, 1, where 5 is the eigenvalue. And you can also verify this for this eigenvector, which corresponds to this eigenvalue. So effectively, we have 2 and 1. So the eigenvector looks like this. So the eigenvalue can effectively stretch the vector if it's greater than 1, compress it if it's less than 1, or negate it if it's negative. But the vector is always going to stay on this line through the origin. So effectively, multiplication by A is a transformation that maps each eigenvector of the matrix A, in this case in 2 space, along the same line through the origin, which is the eigenspace of A. If E is a positive integer and lambda is an eigenvalue of matrix A, and V is a corresponding eigenvector, then lambda to the power of e is an eigenvalue of a to the power of e, and v is a corresponding eigenvector. So this can be seen from the following equation, where we have a by v is the scalar lambda by v, and if we multiply both sides by a, we get AAV, which is a scalar by AV, and AV is lambda v. So on the right hand side, we get lambda squared by v. And on the left hand side, we can write AA as a squared. And if you continue this process, we get lambda to the power of e on the right hand side, and a to the e on the left hand side. So in our case here, if we square a, we're just multiplying a by itself. So we get 9 plus 8 is 17. 12 plus 4 is 16. And 6 plus 2 is 8. And 8 plus 1 is 9. So the eigenvalues of this matrix A squared is obtained by squaring the eigenvalues of A. So we get lambda 1 squared is 25. And the other eigenvalue squared is 1. And we can show this manually. So if we suppose this is our matrix B, multiply by V is lambda V. So the characteristic equation is the determinant of B minus lambda I. So that gives the determinant of 17 minus lambda, and then we have 9 minus lambda on a diagonal, and 16 and 8 off diagonal. So we expand this to get the characteristic polynomial. So 17 minus lambda by 9 minus lambda minus 16 by 8 is equal to 0. So if you multiply this out, you get lambda squared minus 17 lambda minus 9 lambda is minus 26 lambda. And then 17 by 9 minus 16 by 8 is positive 25. And that's equal to 0. And you can see that when we factorize this polynomial, we get lambda minus 25 by lambda minus 1 is equal to 0. So therefore the eigenvalues for our matrix B, which is equal to A squared, are 25 and 1, as we got by squaring the eigenvalues of A. And I'll leave it for you to verify that the eigenvectors are going to be the same as the eigenvectors corresponding to the eigenvalues of matrix A.